Now let's look at some examples and see which outcomes are sequentially consistent and which outcomes are impossible under sequential consistency. First of all, we'll take a look at two code sequences, one for P0 and one for P1, and both variables are initialized to 0. The first process executes A equal 1, B equal 1, and the next process prints B and A. Note that the program is non-deterministic due to a lack of synchronization. That means that it might print different values for A and B depending on the order in which the statements execute. So, assuming that our memory is sequentially consistent, which values might possibly be printed for A and B? Answer the questions in the quiz below. And then, given that those values are possible, what values for A and B are impossible with sequential consistency? Okay, how do we prove it? For A to print as 0, we have to have S4 preceding S1. Otherwise, S1 would set A equal to 1 before S4 printed it. One statement ordering that will achieve this is S3, S4, S1, S2. In other words, P1 executes both of its statements before P0 executes any of its statements. Now, for B to print as 1, S2 needs to precede S3, because only then will the value of B be set to 1 before it's printed. And an example is the sequence S1, S2, S3, and S4. Well, if we want A to print as 0 and B to print as 1, both of those conditions should hold, but they can't hold simultaneously. We start out with assuming that S4 comes before S1 because A had to be printed as 0. But we know that S1 has to come before S2 because our assumption is that the statements execute in program order. And also we know that S2 has to come before S3 because B printed as 1. Of course, S3 has to come before S4 because that's program order. So now we have a condition that says that S4 has to precede S1, which has to precede S4, and that, of course, is a contradiction. So the outcome A and B equals 0, 1 is impossible with sequential consistency. But if we didn't have a sequentially consistent machine, the outcome A, B equals 0, 1 would in fact be possible. Think about what statement ordering can produce it. Let's say that S2 executes and then S3, and S1 hasn't executed yet, so right away that violates sequential consistency. S4 executes after that and then S1. And if these things happen in that order, then A will be set to 0 because A gets printed before S1 sets it to 1, and B will print as 1 because S2 happens to set B to 1 before S3 prints it. In this case, which of the two sequential consistency precedence hypotheses above is violated? Well, it's the program order expectation because S1 doesn't come before S2, but according to program order it should. Let's take another example. In this example, P0 has statement S1 which sets A equal to 1 and then prints B, whereas P1 sets B equal to 1 and then prints A. So each process sets one variable and then prints the other one. We want to assume, as usual, that A and B are initialized to 0 and decide which values can be printed under SC and which can't. And then we want to prove that the impossible results can only occur if SC is violated. The program is non-deterministic because it could print different values for B or A depending on which order those statements execute in. There are no synchronization statements that make sure that one variable is set before it's printed or vice versa. So with sequential consistency, we still have the program order guarantee. S1 must precede S2 and S3 must precede S4. And then if we have several different orderings of statements, then we can get several different results. Now on a non-deterministic machine, the other outcome AB equals 0, 0 is possible. How can this happen? Well, one way that it can happen is if we execute S4, S1, S2, and S3. In that case, each variable is printed before it's set, but that violates the program order expectation for P1, namely S3 and S4 execute out of order. Another way is if we execute S2, S3, S4, and S1, and then we print B just before it's set to 1, and we print A just before it's set to 1. In this case, we had to execute the statements of P0 out of order. Both of those examples are non-deterministic, and non-deterministic programs are hard to debug. But sometimes non-determinism is actually useful in a program, because if you try to make a program too deterministic, sometimes that'll slow it down. And if you get reasonable non-deterministic results, depending upon which order the statements execute in, you can write the program in a way to speed it up and take advantage of non-determinism to save you some time, still getting reasonable results. So if that's the case, does preserving ordering of memory accesses matter? Well, it doesn't matter where we can tolerate non-determinism, but otherwise it does matter because it's easier to debug, and it makes sure that if programs are synchronized, then the synchronization will work as it's supposed to.